What if your brain could not only control a device but sense when something goes wrong and correct it in real time? In today's special BCI Award series episode of Neurocareers, Doing the Impossible, we dive into breakthrough in neurotechnology that pushes the boundaries of human-machine interaction. We're joined by Camille Gontier, a researcher at the Rehab Neural Engineering Labs of the University of Pittsburgh, to explore his BCI Award-nominated study, Endogenous Modifications in M1 Activity Allow Online Error Detection and Correction in Human BCI. Camille's research tackles one of the most challenging questions in brain-computer interface design. How can we enable the brain to detect its own errors during BCI control without any external feedback and then self-correct on the fly? In this conversation, we will aim to cover how endogenous signals in the primary motor cortex M1 reveal internal error monitoring, why this mechanism is crucial for improving the reliability and autonomy of BCI, what this means for the future of neurorehabilitation and assistive technology, and, of course, Camille's own journey from France to Pittsburgh at the intersection of neuroscience, engineering, and innovation. So, are you ready to discover how the brain can correct itself in real time? Let's begin. Welcome, Camille. It's a great pleasure to have you on our podcast. Thank you so much for coming. And can you please introduce yourself and let our listeners know where you're joining us from what part of the world at this time?
Sure. Well, thanks a lot. First of all, thanks a lot, Milena, for the invitation. It's a real pleasure to have a discussion with you. So, as you said, my name is Camille. I actually just recently finished my postdoc at the Rehab Neural Engineering Labs of Pittsburgh, and I just started a month ago a new tenured position back in France. So it's a brand new position that I'm starting now. And right now I am talking to you from Strasbourg in France. So this is a big city exactly at the border between France and Germany. And this is here at the University of Pittsburgh that I just started my new tenured position at the INRIA. So that stands for the National Institute for Research in Machine Learning. And yes, this is where I just moved 1 month ago.
Oh, congratulations on your new position.
Thank you.
Yeah, that's wonderful. And actually, I have experience giving one of my first invited talks. It was done in Frankfurt. It was a congress dedicated to studies of the brain. And I remember that it was very strict how people were crossing the road. So you wait until there is a green light and then you cross. And then actually in 2 weeks, I had another invited talk. It just happened this way. And it was, I think it was in Strasbourg. It was a little further. It was like a little place, Rofetch, but I hope I pronounce it correctly. But I needed to stay several days in Strasbourg. And I'm standing, at the intersection and waiting like I already used to do in Frankfurt. And people just cross the road. They don't worry. And I say, how come? It's just I was in Frankfurt, not far away, and people are so strict. And here people are just walking. You say, of course. Here we don't have any problems like that. We walk, when we can.
Yeah, it's true. There is some kind of cliche saying that the closer you get from Germany and Switzerland, the more people are likely to be very respectful of traffic laws. While when you get away from it and you go further into France, people are a bit more relaxed when it comes to jaywalking. I'm not sure this is 100% true. Probably statistically, you might have a significant difference between the two populations.
Yes, at least from my personal experience, it was the case. Yeah, but it's a beautiful place.
It definitely is, yes.
Yes, very interesting. And you had a career transition, and where discussing this in our podcast, this early career transitions and where to go. So I think we have so much to discuss with you. Maybe we can start with the project. Yes, first of all, the BCI project. Maybe you can explain what was the goal. How did this topic originate? Why did you decide to specifically work on this project? And then we will get into further explorations.
Sure. So what I suggest I can do is just do a very short presentation of the methodology and the project, and then put a bit more of context and explain where it's coming from.
Yes.
And especially explain the novelty or maybe also the lack thereof. That is to say, to explain that previous studies had already done stuff that are pretty similar.
Yeah.
So the idea of the project is to try to improve and augment the accuracy of human BCI motor control. So I guess this is a BCI podcast, so correct me if I'm wrong, but I guess the audience is pretty familiar with brain-computer interfaces.
Yes.
Okay. So what we did at Pittsburgh is that we have, well, the people at Pittsburgh, they have a great chance and a great opportunity to be able to work with human participants. So at the moment, 3 human participants suffering from tetraplegia who have been trained to use a motor brain-computer interfaces. That is to say, they have electrode arrays into them the M1 cortex, recording the activity of the motor neurons in real time. And then there is a rig with an ad hoc algorithm that transforms this neural activity into a movement. A movement of what? Well, it depends on the setup. It can be the velocity of a cursor on the screen. It can be the displacement of a prosthetic arms.
Mm-hmm.
But to keep it simple, here we mostly focused on 2D cursor control. So the participant is just controlling a little cursor on the screen to reach for a target, to click, to grasp the target, and stuff like that. So very, very basic stuff. So people from the audience are pretty familiar with this setup, I guess. And also people might know that also control of BCI prosthetics by a human can be pretty impressive. I mean, it's super impressive to see a human participant being able to control a cursor and to reach for a target just with his brain. If you're not into BCI, it can be mind-boggling. But still, this control is still not perfect and is still very far from able-bodied performance. If you look at for instance, in a basic task in which a cursor appears at the center of the screen and the participant is instructed to reach for a target at a random position, usually the participant is able to reach for it, but the trajectory is not perfect. And what I call not perfect trajectory is that the cursor is not going to fly straight to the target in a perfect straight line. Most likely, depending on the accuracy of the decoder, on the quality of the signal that is acquired on that day, the trajectory of the cursor might sometimes go into the wrong direction, which degrades the performance of the control, which can be a bit frustrating for the participants. So what I try to do is to come up with a way to kind of nullify these periods in which the cursor is not moving into the right direction. And to do that, we leverage something which is called the error signal. So it has been known for a long time that the brain, and especially the motor cortex, is encoding the motor intent, which is the basis of BCI. But, which is kind of interesting, neurons into the cortex, they are known to have a mixed selectivity. That is to say, they are tuned to many, many things. And especially they are tuned to whether the cursor is moving into the right direction. They are tuned to whether the current movement is correct or not. And this is something that people using EEG analysis had already observed a long time ago. And this is something they call the error signal. If, for instance, a participant controlling a BCI with whatever device, either an intracortical BCI or an EEG-based one, so if he's controlling a cursor or prosthetics, and if the cursor does not appear to go into the right direction, either because of faulty decoding or because the nasty scientists are inducing some kind of bias to trick the participants into committing a mistake, well, the brain is going to react to it. When the participant is seeing that something is off, the brain is reacting to it in the way that there is some very specific neural signature that appears into the activity T of M1, and that can be detected, and that a lot of previous studies have used to be able to classify trials, whether they are good or they are faulty, and to classify control, whether the participant is seeing the feedback of the faulty control or not. So there is a signature from the motor neurons that can be detected and that can be leveraged as a signature of the participant feeling that the cursor is not going into the right direction. So the idea of the project was to complement classical motor decoding by having a classifier which is able to detect this kind of error signal and use it as a signal for the BCI setup that something is not going right. So the both loops, they go in parallel. The first one is just a classical motor decoding, just like in any classical BCI setup. And at the same time, we trained a classifier, which is solely using activity from the motor cortex. And being fed with this M1 activity, is classifying each time epoch as whether the cursor is going into the good direction or not into the right direction. And if we are in the latter case, we can perform error modulation, implementing some kind of short circuit on the motor decoding. If the classifier is detecting that the cursor is not going into the right direction, we can either slow down the decoded movement of the cursor or cut it off entirely to prevent the cursor from moving further away from the target. That's the main idea of the project. And so the idea was to perform this kind of classification first with offline data, to be able to precisely analyze what kind of difference there are in the activity of the brain between periods of good and bad control, and finally to implement that with real human participants and to see whether it really improves performances. So this is the main idea of the project. It's not extremely novel, actually. As I said previously, this error signal had already been identified for a long time, using different kind of modalities, using EEG, using ECOGs, using intracortical recordings. And previous studies had already tried to leverage that to be able to perform error modulation. So I'm thinking of different studies for other labs, which we are putting into our paper. So I would say our novelty is mostly incremental. We are taking this idea, which per se is not novel, the idea of using this error signal to be able to augment the quality of BCI decoding, and we bring a set of novelties. We bring different theoretical analyses. We are checking whether we can detect this signal more or less rapidly, a bit earlier than in previous studies. And as far as I know, we are the first one to implement this idea, this error modulation, with human participants, while most previous studies were doing that with non-human primates. So yeah, it's not a very novel idea. We are just trying to improve it incrementally.
Yes, beautiful. And it's beautiful even to get an understanding that we have a mechanism that tells that something is going wrong. Yes, the intent does not correspond to the actual result.
Mhm.
And we can use the system if we can learn how to read the signal. Yes, and then correct it in real time. As real as, of course, we can do it.
Yes.
And also you mentioned that you were working on improving the speed of this process, yes, of how quickly we can react.
Mhm.
And in fact, it is very interesting to understand how quickly this process of the error detection happens in our brain.
Mhm.
And then how long does it take to us to react and to make action to do something about it if it is not going into the right direction? Can you give us a perspective on those speeds? How does it all work together?
Yes, sure. So I've been talking about previous studies which have been studying and analyzing this error signal. And usually this signal is assumed to be purely exogenous. That is to say, it is thought to be just a reaction of the feedback of the participant seeing the error. That is to say, the participant is controlling something, and if sees that the cursor is not moving into the right direction, they are going to see it, and the brain is going to react to this signal. So when I say it is exogenous, it means that it's just a reaction from a visual feedback of the action not being right. So this has been studied either by just focusing on neural activity after the onset of the error, or by artificially inducing errors. That is to say, we just give the participant control to a cursor, and from time to time, the scientists are going to switch a knob, which is going to modify the control and induce artificially some error. And so the participants are going to, they don't provoke this error, but they are going to react to the visual feedback of the cursor not going into the right direction. So this is why this error signal is usually assumed to be just a visual feedback that follows the error. So this error signal is usually thought to be the consequence of the error. The main problem is that if we were to use this signal as defined previously in a BCI, it means that we need to wait for this error to be perceived by the participant before we can correct or do any modulation. And the point is that ideally, we would like this error to be detected as early as possible. So time that is required for this error signal to be perceived and detected by the participant, it's basically dependent on the modalities. For the slowest modalities, I am thinking about previous studies that used non-brain related signals, for instance, the size of the papilla or the heart rate variability, to see whether there was a signature of this error signal into this matrix. It is, but it can be pretty long. For instance, the pupil diameter needs at least half a second to be able to be detected as a reaction to an error signal. So we try to go a bit faster, and especially to see whether this error signal could be not just the consequence, but maybe the cause of the error. Because it might be, we know that the activity of M1 is very variable, and especially the tuning, the mapping between M1 activity and the intended velocity can change rapidly over time. And we wondered whether it's possible to get a sense of whether this error signal might be something that can already be detected before the onset of the error, and to detect not something that is the consequence of the error, but its cause. It turns out that it's pretty difficult to do so, because the definition of good and bad control is simply based on the distance between the cursor and the target. Ideally, this distance should continually decrease, but we define bad control as periods in which the distance is increasing, the period in which the distance between the cursor and the target is increasing, meaning that the cursor is not going towards the target. But it's very difficult to be able to identify endogenous and exogenous signal simply because the participant might be able to feel that the cursor is going to overshoot or to move away from the targets before it's actually going to be. So the point of our analysis is to show that it's possible to detect significant changes of M1 activity slightly before the onset of the error, but it's very most likely due to the fact that the participants themselves are feeling that the cursor is going to move off target. So it's still something that is feedback related, but due to the fact that the participants are anticipating that the cursor is going to move away before the definition of the error is setting off. But yes, the idea is that we are already able to detect a neural signature of faulty control, something 80 milliseconds before its actual onset.
Yeah, that's very interesting. So basically, you are trying to detect that more endogenous component even before the person received that visual feedback, but already knows that it's going somewhere, not where it's supposed to.
I would be a bit more prudent about using the word endogenous, simply because it turns out that it's very hard to define and to decipher what is endogenous, what is exogenous. We prefer to say that it's possible to detect some kind of neural signature that is taking place before the onset of the error. Whether it is endogenous or exogenous is not super clear, but our analysis suggests that it's still something that is feedback related.
Yes, yeah, I agree. And it's always questionable, endogenous, exogenous. Yes, there can be a lot of conversation about that. But okay, very good. Now, what was the result of your study? What did you get?
So the result we were the most exciting about was indeed to check whether error modulation, as we call it, is going to be useful for human participants and is going to be able to improve the performance. I'm saying that this is the results we were the most excited about because this whole framework had already been tested with monkeys, and this was the first time testing it with humans, as far as I know. And so we were excited to see whether it was indeed going to improve the performance. It turns out that it did, with a little twist. So to measure the performance of human participants at controlling a cursor and doing a task with it, we cannot simply just look at the trajectories and say, oh, it looks good, or just ask the participant, hey, did it feel good? Yeah, yes, it did. No, we have to use some quantified metrics. And the kind of metrics that we came up with, this is, for instance, the proportion of correct trials during an experimental sessions. This is the length of the path followed by the cursor, because we want this trajectory to be as smooth and as direct as possible. So anything that takes longer than expected is going to be a sign of bad control. We are looking at the target acquisition rate. So not only the number of correct trials, but also the number of correct trials per unit of time. And also some more subjective metrics, such as the subjectively reported difficulty reported by the participant. What's exciting is that we saw improvement in most of these metrics and across most of the participants, except for one, which got non-significantly degraded by our method, which is the target acquisition rate. For all other metrics, we see improvement. That is to say, if you just look at the trajectories, it is less wobbly and more straight to the target. And it feels like we're indeed able to nullify the components of the trajectories which degrade the performance. But it took the participant a bit longer to reach the target. So the trajectories are better, they are more accurate, but they take longer, which intuitively makes sense because the task does not require the participant to be extremely precise. You just have to reach for a target and it doesn't really matter if you overshoot it. But this error modulation comes at the cost of a reduced velocity for the cursor, because the way it works is that our classifier is detecting whether the cursor is going on or off target. And if it detects that the cursor is going away from the target, it just reduces the velocity to prevent the cursor from moving super fast further away from the target. So overall, it comes at the cost of a reduced velocity during periods of detected error, which might slow down the trajectory of the cursor. So what we thought of that is that actually this framework, this error modulation framework, might be especially useful, not in tasks in which you just have to reach for a target without a lot of accuracy and when you don't need to be very precise. But it might be especially useful for tasks in which you need to be very precise. For instance, when you need to stop above a target, to grasp or to click it, or to be very precise. So this is why, after testing our framework in a classical 2D center out and reach task, which doesn't require a lot of precision, we also tested and implemented it in other tasks in which the participant needs to be extremely precise and to be able to remain idle above a target. So the first task was something that we call the helicopter rescue task. So this is a gamified task in which the participant still has to control a cursor, which is shaped like a little helicopter, and he has to hover all the way to a target, which is gamified like a scared emoji, and he needs to click and grasp it and bring it back to the center. So it's way more difficult than the previous one because you cannot just fly super fast and overshoot the cursor. You have to be able to remain idle over it to click it and bring it back to the center. So for this kind of tasks that require a bit more of precision, we did see an improvement in the target acquisition rate. Mm-hmm. And similarly, we try to see whether this error signal that is picked up by the classifier is sufficiently robust to be used in more realistic and more complicated tasks. So we applied it to the BCI tasks of the recent Cyberslon competition. So I'm not sure the audience is familiar with the Cyberslon. This is basically the Olympics of BCI. And it involves a set of BCI tasks in a gamified environment, like being able to control a wheelchair in a maze, being able to click on specific elements on a keyboard. And especially there is a task, which is called the ice dispenser task, in which the participant needs to control a little arm holding a goblet and to maintain it idle under an ice dispenser. And to maintain it idle so as not to slow down the process of ice dispensing and not to spill the ice. Mm-hmm. So the difficulty is not only to be able to control the arm, but also to be able to remain precise and not to move around away from the area of interest. And we also play around with error modulation in this setting. And here too, it allowed us to improve the performance as computed by the time needed to complete the task for the participant. So it was pretty interesting to see that we are indeed able to see some significant improvements, also small ones, also incremental ones, in tasks performed by humans in different environments. Once again, there is no extremely strong novelty. The improvement is still incremental compared to previous studies, but it's still nice to see that we are in line with previous studies and to be able to slightly improve them by applying this framework to different tasks.
Yes, absolutely. And sometimes those incremental changes, but they lead to a great progress. Yes, so of course, that's very, very interesting. And what electrodes were used to record the data? Were these intracranial recordings, depth electrodes, or surface, ECOG electrodes? What type of?
Yes, it was intracranial. So basically UTA arrays.
UTA arrays.
Two of them which were located into the motor cortex.
What was the most challenging part of the study now, looking back?
I would say that for me, the most challenging part, it was not a scientific or a technical challenge. It was more a matter of personal frustration. I'm really putting the emphasis on the fact that we are not creating a huge breakthrough. This is not something that is insanely novel, in that previous studies had already done stuff that are pretty similar. What was frustrating at some point for me, but from which I learned a lot, was that I was not really aware of these studies. So when I joined the lab, I had a lot of freedom to look for different possible solutions. So Jennifer Collinger, the head of the lab, was extremely welcoming and extremely helpful. We discussed some problems on which I could work. I spent some weeks playing around with data, trying some new solution, and at some point I came up with what I thought to be a very novel and very great idea. Oh, I have this insane idea. I'm going to build a classifier, which is going to be to work only using neural data, and which is going to be used to detect periods of bad and good control. So I tried to play around at first with offline data, and it worked. I was able to build a classifier which is able to tell apart periods of bad and good control. And at some point, Jen Collinger came to my desk and said, "Hey, have you looked at the last issues of the Journal of Neural Engineering? Because there is a paper that does something pretty similar." And yeah, that was a paper from another lab doing exactly this idea of error modulations in monkeys. They've been able to build a classifier that is picking up on neural activity to tell apart periods of bad and good control, and to use that to improve the performance of BCI control in monkeys. So when I saw that, I was pretty pissed, and I think I dropped a pretty loud F-bomb into the lab. I had the impression that I have been scooped, and it was pretty frustrating. But I mean, this is the way science works. I don't remember which philosopher said that if you have the impression to have a good idea, it means that someone else already had this idea previously. And it was a very humbling experience. So with Professor Collinger, we worked together to highlight some other novelties and to improve incrementally what the previous studies have done. So in the end, it made me realize that you don't always need to go for something extremely novel, that you need to acknowledge that your peers have been doing previous studies which are really great and that you need to acknowledge, and that it's okay to slightly improve them incrementally. But still, you need to acknowledge that what you do is probably not extremely novel, and you need to acknowledge what previous labs and previous studies have managed to accomplish.
Yes, and I really value your transparency. So you said exactly as it is without trying to embellish, something and negate the stuff that other labs have done. And it actually shows, I think, your ethics in general in research. And I think that's very, very valuable. And also understanding that, yes, although there were some studies that were of similar kind, but we have these certain novelties that are still bringing us forward towards better BCI control. And that is very important. So, yeah, thank you. Thank you very much for that.
Yes, I think it's very important to acknowledge what previous people have been doing, and more generally, as you said, to have a strong ethics when you do science.
Yeah.
This is something that my PhD advisor told me right at the beginning.
Mhm.
Don't try to oversell your results. Don't try to hide mistakes. Don't try to do p-hacking. It might be common sense, but sometimes people just still do it. Never do that because it's always going to end up flying back in your face. It might be some common sense to do good science, to have some ethics, but sadly it is sometimes overlooked by some researchers.
Yes.
And speaking of that, I would like to take this opportunity to give a big shout out to my two mentors. So my PhD advisor, it was Professor Jean-Pascal Pfister at the University of Bern, and my postdoc supervisor, Professor Jane Collinger at the University of Pittsburgh. Both of them were insanely welcoming, insanely helpful. And if people are looking for PhDs or postdoc, just go for these labs.
Thank you so much for this shout out. And yes, people are definitely looking for PhD positions, and those are amazing places. I collaborated at some point with Dr. Wei Wang, but it was a long time ago. He worked at the University of Pittsburgh on motor brain-computer interfaces, but then he decided to follow his path into a medical field, and now he is, I think, a neuroradiologist. But I always hear wonderful things about the University of Pittsburgh and the research that is done there. So thank you very much for all this information. And what would be your next step, next development in this area if you would continue? Because now, as I understand, you moved to a different place and probably pursuing slightly different area of research because there are different resources at different places, yes? And the University of Pittsburgh has a pretty unique setup. So what would be your next step if you would be able to continue this line of research?
Yes, so basically what I'm going to do here at the University of Strasbourg, I believe this is still considered to be BCI, but this is completely different from what I've been doing in Pittsburgh. So as you said, in Pittsburgh, they have an amazing setup and they're doing great science with human participants. And what I was doing with Jane Collinger at that time, it was mostly intracortical recordings and for motor decoding. So I guess this is a classical definition of BCI, and this is usually what people think of when you talk about BCI. That is to say intracortical recordings for motor decoding or sensory stimulation. So what we are doing here in Strasbourg is, it's widely different. We are going to do closed loop neuron modulation for application to psychiatric disorders. So there are several differences. The first one is that it's at the beginning, at first, mostly going to focus on non-invasive technologies. So non-invasive technologies for both recordings and stimulation. That is to say, most of the recordings is going to be done with EEG. Most of the stimulations are going to be done with TMS or current stimulations. So for the moment, only non-invasive stuff. The second difference is that instead of focusing on motor decoding or sensory stimulations, as people in Pittsburgh are doing, we are going to focus on neuromodulation for psychiatric disorders. It has been empirically shown that electrical or magnetic stimulation of the brain can yield improvement in some symptoms and in some pathologies. I would say the most widely known example is deep brain stimulation for Parkinson's disease. You put an electrode into the brain of the patient, you elicit some stimulation, and probably not no more, but reduce tremors and improve gait movement, which is super impressive. And there is a line of research trying to see whether different kind of modulation can also have effects on other kind of disorders. I am thinking, for instance, about being able to stimulate brain activity to increase or reduce the activity into some frequency bands of the EEG to be able to solve some symptoms, for instance, for Alzheimer's disease or for ADHD. So there is a whole line of research trying to do neuromodulation and to apply it to psychiatric disorders. I would say that the main issue at the moment is that it's very empirical. There is no clear quantitative insights as to what kind of stimulation is going to elicit what kind of activity and improve which symptoms in which way. For instance, in deep brain stimulation, it is still pretty much empirical. You put an electrode at some location and you apply some kind of pattern of stimulation and you obtain some kind of improvement. So what we would try to do is to have efficient closed loop neuromodulation in the sense that we would like to have on-the-fly improvement of the stimulation. That is to say, at each time step, being able to detect the effects that stimulation at previous time steps had, and to be able to refine them on the fly to converge to the desired effect. So a widely different field of research, still very open, still in its infancy. I would say it's still considered to be BCI because it still involves decoding of some mental states and ad hoc stimulations in a closed loop manner. And what is going to be exciting about that is that it's going to mix both very interesting clinical applications and also very exciting theoretical challenges. We need to be able to stimulate in silico the effect of stimulations on the brain, and we need to be able to perform active learning to close the loop and to be able to optimize it on the fly. So I'm really looking forward to it.
Yeah, it sounds absolutely exciting. And yes, we know that lately we have a rise of neurostimulation and its applications. And like you said, for Alzheimer's disease, patients with dementia in general, for improvement of their cognitive functions, and of course, people with neurodevelopmental disorders. And so there are so many amazing applications. And yeah, and the field, I think, is just starting. Yes, it's the right place to be here. My question is, what skills, what things learned from your current project that at the University of Pittsburgh, or the project that you finished, you can use for your new work? Anything from what you already learned during the process you can apply in your work on this neuromodulation for psychiatric disorders?
I think my answer is going to be very brief and uninteresting. I don't know. I'm not absolutely sure. So for sure, during this postdoc in Pittsburgh in the lab of Jen Collinger, I learned an insane amount of stuff about BCI, about how different methods work. And when I say methods, I mean both hardware and software. What are the best way to do classification? What are the best way to do decoding? As we speak, we still have an ongoing project between the University of Pittsburgh and the University of Bern in Switzerland, in which I did my PhDs, in which the University of Pittsburgh is doing some recordings, and the theoretical people at the University of Bern are playing around with different new nonlinear methods to do motor decoding to see whether we can improve previous methods. But at the moment, which specific elements of this huge background of stuff that I've been able to learn in Pittsburgh are going to be especially useful for these neuromodulation projects, I'm still not sure. Simply because this is a project that I just started just a few weeks ago, and it's still not clear in which direction we are going to go. But what is clear is that I now have a clear idea of what kind of methods can be used for decoding of mental states, whether it's better to use linear methods or nonlinear methods. Each method has its perks and its inconvenience, and especially what it's like to work with human participants. So I definitely learned a lot in Pittsburgh. I'm not sure what and all these elements are going to converge and contribute to this new project. The main idea is that everything that I've been learning, either with Professor Pfister during my PhD or with Jen Collinger during my postdocs, are going to be invaluable. And I would say there are a lot of soft skills, like being able to think efficiently about different methods, which it's hard to put words on, but it's definitely going to be useful for the rest of my career in research.
Yeah, it's also not only about skills, it's about the mindset. Yes, how you think about things. Yes, and thank you very much for noting that. Yeah, it is very important. And as we have a career-oriented podcast, I would like to ask you several questions about your career path. We see the trend of people going to the industry instead of staying in academia. And you are actually staying in academia. Yes, you finish your postdoc, and now you have another position in which you will be working on developing these methods, yes, for neuromodulation, for psychiatric disorders. What makes you want to continue on this academic path?
Oh, I would say it's a good question. Maybe I should start by saying that the French system of academia is widely different from what exists in different countries. I would say that in most countries, including the US or Switzerland, for instance, it's very hard to find a tenured position and to remain in academia once you have done your postdocs, simply because you have way more postdocs than tenured professor positions, and it can be really hard to stay in academia. The way these classical systems work, for instance, in the US, is that you do your postdoc, and then you have to wait to find a position. And usually when you find a professor position, it is not tenured yet. So you become a professor, you have your team, and you have a full package with standings and stuff. But still you need to wait a little bit before being tenured. The French system is pretty unique and works exactly the opposite way. That is to say, regularly, universities and research institutes are going to organize competitive examinations to recruit researchers once they are done with the postdocs. And once, if you succeed in this competition, you get tenured, but nothing else. So this is basically my position, which is called, well, you have different kind of position, but basically the kind of stuff that I have, this is called being a chargé de recherche. The idea is that you are a civil servant and the position is a lifelong postdoc position. So de facto, we are tenured, but without any other perks. That is to say, I don't have my own team. I am not allowed to be the sole supervisor of a PhD student. I cannot apply to big grants. But the French system works that way, in that once you have this tenured and nothing else position, after a few years, usually less than a decade, you pass some kind of mega PhD defense, and then you become a full professor. And then you're able to have your own team and to have to apply for big grants and that kind of stuff. So I really like these two-steps systems, which allows people, it's still very competitive, but at least it allows to hire a lot of postdocs and to make sure that a lot of postdocs are going to find long-term position in academia, even if they don't want to become full professor by the end.
That is very unique. I never heard about this. Yes. And gradually you can apply for smaller grants, yes, building up. What is that outcome that you will need to present in 10 years? You said like the big defense. What is that? What do you need to have prepared for that defense to get a full professor position?
So once again, maybe my answer is going to be a bit disappointing. I would just like to explain that this is my first time being back in academia in France, and I'm actually not very familiar with the French academic system because I did my master in France, but then the PhD in Switzerland and the postdoc in the US. So there are still some elements that I still don't perfectly master. But basically, the idea of this super PhD defense, which is called an habilitation à diriger des recherches, the idea is to show all the results of the previous PhD students that you have contributed to supervise since you got tenured. So from what I understood, it is mostly going to be to focus for sure on your own results, but also on your teaching and on the results that the PhD students that you help to supervise have been able to obtain.
Yes. So you mentioned it's like habilitation procedure. Yes. We had it. I'm originally from Lithuania, so we had habilitation procedure.
Okay.
It's you of course you defend your PhD and then you work and then at some point you do your habilitation. And I think in Germany there is also habilitation doctor or something like that.
Yeah, I'm not sure. Probably, yeah.
Yes, very interesting. Now, I would like to dive in a little bit into your past and see how did you come to this place where you are working on invasive brain-computer interface and now moving to non-invasive. How did this all start? When did you already know that this is what I want to do and I'm going towards it?
Maybe once again for the third time, not a very interesting answer. I don't know. No, I'm going to explain from where I'm coming from. The idea is that I never had a grand scheme in mind. I never told myself 10 years ago, okay, in X years I'm going to do that, and then I'm going to do that, and then I'm going to do that. I think a lot of people have this kind of grand scheme, very ambitious scheme in mind, which is very good. but most of the time, your career path is going to be so dependent on small contingencies that usually I find it more efficient to do what I would call myopic optimization. So just try to optimize one step at a time. Okay, I am in this position at time t. Which action should I take to maximize my happiness just at time t plus one? And I'm only going to look at time t plus one and not several years into the future. So this is why when you look at my CV, I might have done a lot of unrelated stuff, but it's just that at each time step t, this is what I felt to be the most interesting. So I started my academic journey in 2018. I started my PhD in Switzerland at the University of Bern in the lab of Professor Pfister. At that time, in a lab that does absolutely no BCI. This was a lab doing theoretical neuroscience, so mostly focusing on a normative theories of how the brains and cells are working, mostly developing mathematical models of how synapses are working and confronting them to observations. We were in a team with different labs. So I was in the theoretical neuroscience labs. There was a computational neuroscience team. There was a team doing neuromorphic hardwares and computations. So we are still doing neuroscience, but most of us had backgrounds in physics, mathematics, engineering, very little biology. And yeah, so the idea was that I did my PhD. I had the impression mostly to do a PhD in physics or in statistics, but with application to neuroscience. And actually, Professor Pfister is a physicist and a theoretician by training. But what is very interesting is that he has close ties with a lot of experimentalists. And especially my PhD co-advisor was Professor Martin Müller from the University of Zurich, who is doing recordings. And what my PhD supervisor told me was to build theories with him and then to confront him to the recordings and the observations from the team of Martin Müller. So this was very interesting. My whole PhD was trying to develop methodologies and theories and to confront them to observations. And I think I kept this idea of being a theoretician and a computational neuroscientist by training, while still trying to build quantitative solutions for concrete biological problems. This is what I like to do in academia, having a theoretical background, but making it useful and applying it to concrete biological and clinical issues. So this is what we did during my PhD. Basically, we came up with algorithms to optimize the way we study synapses. And hopefully, this is what I did during my postdoc in Pittsburgh, in which we used different theoretical methods to try to improve the accuracy of BCI control. And I've been able to do this postdoc thanks to the help of the Swiss National Science Foundation. There's a call for a grant, which is called the Postdoc Mobility Grant, which is open to anyone who did their PhD in Switzerland, and which allow them to have their salary paid to do a postdoc for 2 years abroad. This is a very generous funding scheme, which I applied for, and with the help and the supervision of both Professor Pfister, or as a PhD supervisor, and Professor Collinger as a would-be postdoc supervisor, I've been able to get this grant and to spend 2 years in Pittsburgh. And then finally, while I was in Pittsburgh, I applied to different tenured positions back in Europe. I ended up being able to join the INRIA, this Institute for Research in Artificial Intelligence here in France, and to still work on building theories and using computational neuroscience to solve clinical issues.
Yeah, that is amazing. And thank you so much for pointing that we don't always need a grand schema. Yes, to build our career and build it successfully. And we can take those gradual steps. Yes, like small contingencies, like you mentioned. And it's actually, has some parallel to the research you've done, let's say, at the University of Pittsburgh. Yes, those gradual improvements, but at the end, they lead to wonderful results. And I think that's very important to know to our listeners who are building their careers, because sometimes people worry, I don't have this grand schema of my life yet. And maybe you don't need to. Yes, some people do, and that's okay. But some don't, and that's also okay, because there are different ways for us to build our careers.
And I really appreciate you saying that there is a parallel between this approach and the way we do science. Actually, I would like to recommend a book that I found to be extremely inspiring. It's called Why Greatness Cannot Be Planned. It is by Joel Lehman and Kenneth Stanley. And it's about precisely how science is not about having extremely ambitious project and grand scheme, but mostly work by what they call stepping stones. So science just works one small stepping stones at a time. And the kind of example they give to explain that is that if you were to travel back to the Middle Age and to gather the most brilliant minds of the time and to tell them, okay, you have infinite time, infinite resources, build a computer or build a rocket or build a nuclear plant in the Middle Age, they're going to fail. Even with infinite time, they're going to fail at some point, simply because it's impossible to say, okay, I'm going to build a rocket from scratch. I'm going to build a nuclear pile from scratch. It's just a succession of seemingly unrelated stepping stones that were discovered maybe randomly, that at some point were brought together to create something great, which was not planned at the beginning. And I like to draw a parallel between the way we can consider research that way and the way I try to optimize my different career steps.
You mentioned that now you work at this institute that focuses on the development of AIs and their application actually in healthcare. And of course, that is a whole topic on its own and very relevant. And I would like to explore it a little bit more. First of all, what are, in your opinion, with your knowledge, what are the main clinical or healthcare applications of AI that we may be able to see in the next, let's say, 10 to 20 years, where this field is heading?
Well, I'm mostly going to focus on the application of these new machine learning methods to BCI. Well, the use of new deep neural networks to perform motor decoding and to use BCI, this is something that I am extremely interested in. I would say that until recently, the field was separated into two subfields. There was a field of machine learning and what we call AI that provides a lot of great solutions, which are often pretty complicated. They are nonlinear, they might require GPUs to run, they involve billions of different parameters, but they provide great results in theory. The point is that until recently, it was difficult to see whether they're going to indeed improve stuff when it comes to motor decoding in BCIs. On the other hand, you have much older, linear, simpler methods that have been classically used for motor decoding. So in these simple linear methods, I am mentioning, for instance, optimal linear estimation, Kalman filtering, that kind of stuff, which have been classically used for motor decoding. But the question that you might ask is, maybe it's possible to do better, because, Kalman filtering is cool, but it was developed in the 60s. Maybe it's time to move a bit further. So yeah, the idea is that the kind of frustrating landscape is that on the one hand, you have plenty of super cool machine learning methods, which may not necessarily work when you apply them to clinical settings. And on the other hand, you have plenty of well-proven methods, but which are getting a bit rusty when you compare them to the shiny machine learning methods. And recently, for a few years, some labs have been trying to apply these machine learning and deep neural networks-based methods to improve motor decoding. The idea is that classically, you feed the recordings, the neural activity into your decoding algorithm, which is going to output the velocity of the decoder or of the prosthetics. And usually you do that with linear estimation or with Kalman filtering. And the idea would be, would it be possible to replace this Kalman filter with, for instance, an LSTM or a convolutional neural networks? In theory, there are some improvements. I think the field needs to be a bit more convinced that the improvement is going to be worth the move from Kalman filtering to nonlinear methods. I think it's going to indeed bring improvements. The use of nonlinear machine learning methods is ultimately going to improve the way we do BCI decoding. I'm just not sure it's going to be a huge breakthrough, like an explosion of performance, but I think it's still going to be incremental. These new methods, it feels like they perform slightly better than Kalman filtering and linear methods. Not insanely better, but still it's going to move into the right direction.
And what do you think still stops this transition from the old and maybe a little rusty, yes, like Kalman filtering, into those new AI based on nonlinear methods?
I don't think there is anything that blocks per se. It's just that, especially when you work in a clinical settings, you have a lot of inertia. When you have a solution that is already working well, there is a lot of inertia to try to move towards something that might or may not work better, because the only way to see whether it's going to work better is to test it, which involves a lot of time, and time is very precious when you work with human participants. So I don't think there is any blockage. It's just that we probably need to further improve the communication between theory people and clinical and application people. This is definitely something that I am advocating for, and this is precisely this project that we have between Pittsburgh and the University of Bern. The University of Pittsburgh is doing decoding and has a huge setup with amazing human participants. And on the other end, people in Bern are developing state-of-the-art machine learning methods. And what we are trying to see at the moment is whether this and all these machine learning methods are improving the way we do motor decoding. So I don't think there is a blockage per se. It's just taking some time.
Yeah.
And it's fine.
What are the main tendencies in motor BCI and maybe in the whole field of BCI do you see? Where the field is heading? What are the main directions it's taking? And maybe will be developing in the, again, next 5-10 years, in your opinion, from your point of view?
I'm going to be extremely prudent because, as we said about my feedback, I am not per se 100% BCI researcher. I'm coming from theoretical neuroscience, and I just happen to have joined the BCI community during my postdoc. But probably people who have been full-time into BCI since the beginning of their academic journey, they might have different opinions than I do. From my outsider perspective, I would say that the improvements are going to be mostly, once again, incremental. On the software side, to go back to your previous question, I'm still very hopeful about these nonlinear methods. There are some recent papers showing that LSTM, recurrent neural networks, convolutional ones, are indeed able to improve the performance of decoding as compared to previous and well-approved methods. In theory, on offline data, the improvement is pretty impressive. We are still to see that this improvement is very robust and is going to be transferable once you try it online with human participants. But I'm very hopeful, and I think this is definitely the direction that the field is taking at the moment. And in terms of hardware, there is a continuous stream of improvements. For instance, the youth arrays that we mentioned previously, they work well, but they're starting to have some gray hair. I don't remember exactly, but the patent was from 20 or 30 years ago. So they still work well, but the industry is slowly moving towards improving them. And I especially think that having something that is entirely below the skin is going to be very useful. For instance, the Neuralink stuff is very promising in that you don't have any percutaneous stuff popping out of the skulls, which is a huge burden for the participants. So once again, I cannot think of one huge breakthrough which is going to be a game changer for the field of BCI. From my outsider view, I think progresses are going to come slowly, both from software improvements, that is to say, moving towards more complicated decoder scheme, and from the hardware side, by just continuously improving the different engineering methods.
Yes, thank you. And what skills do you think will be required from people who want to join this field?
Well, maybe I'm a bit biased because by training I am an engineer and I mostly did my PhD into theoretical and computational neuroscience. But I would advise people to try to do as much math and physics and quantitative stuff as possible. Because simply, if you start studying very math-heavy stuff, math, physics, computer science, it's still probably still going to be possible for you to switch to more applied stuff. The opposite can be a bit more difficult. That is to say, starting with biology and clinics, it can be hard with time to get back to math and to physics. Simply because, well, it's probably easier to study math when you are at the beginning of your studies and to then switch to less quantitative fields. The opposite, empirically, I would say, is a bit more difficult.
Yes, I absolutely agree with you. And what opportunities do you think, or maybe you see, are opening for people who want to join the field of brain-computer interfaces?
I am not sure at the moment what these little software and hardware improvements that we discussed previously, whether they are going to increase the number of participants, whether they are going to increase the number of labs. It is something that I hope for. For the moment, the number of labs that do BCIs and the number of participants is very small. It's like the participants are like astronauts. There are just a few hundreds of people who have been into space, and there are just a few hundreds of people who have been using BCIs. So what I really hope for, I'm not sure whether it's going to take place, but what I really hope for is for more labs to open, more participants to be recruited, because this is simply how we are going to democratize these methods and to make them technologies that are useful not only for just some participants in scientific settings, but which are going to be used more widely in a clinical settings. I'm not sure this is going to happen anytime soon, but this is definitely something that I would advocate for.
And maybe you are aware, if not, of course, I understand, if you are aware of the situation in France in terms of supporting neurotech or BCI-based projects, is the grant support, financial support is being stable, decreasing, or maybe increasing as technologies are developing?
I would say the main difficulty that we have in Europe as compared to the US is the possibility or the lack thereof to do invasive BCIs. Non-invasive BCIs is cool, but I mean, any BCI solution has its pros and its cons. With intracortical recordings, you have the activity of individual neurons, and you have an insane amount of information to do fine decoding. But per se, this is intracortical, and a lot of participants might not agree to have some electrodes bumped into their skull. On the other hand, most BCI labs in Europe and in France are focusing on EEG, which is very practical, especially because this is way easier to use to implement for the participants. But you don't have the same degree of quality and the same number of degrees of freedom that you can decode information from. I would say the main difference between Europe and the US at the moment is the fact that it's very difficult to obtain authorization to do intracortical invasive BCI in Europe. I have the impression that this is changing, especially about the University of Grenoble in France, which is developing a lot of ECOG solutions. And I hope that these solutions are going to be more and more widespread. Once again, I'm not sure this is going to take place, and I'm not sure at what pace this is going to take place, but this is definitely something that we are advocating from at the moment. There is the institute I am in as a funding scheme, which is called the PIQ. I don't remember what it stands from, but the idea is that it's a funding scheme that funds very high-risk projects. So classically, funding and grants, they are awarded to, I would not say boring project, but not too risky one. If you come to a funding agency with a crazy idea, with a lot of risk, yeah, you're not going to get your fundings. Precisely, this funding scheme is aimed at very high risk but high possible reward projects. And with some colleagues, we are currently discussing the possibility to apply to one precisely for a BCI setting. To be continued, but this kind of initiative, that is to say, funding high-risk projects, this is definitely something that is really promising, that I am advocating for, and we're discussing the possibility to use one for developing more invasive BCI recordings in Europe.
Yes, I hope that we can meet in a couple of years, and maybe you can give an update of already your new projects and how did this all turned out. And just few questions about the BCI Award for our listeners, for those who are planning to apply. What was the reason for you to actually apply for the BCI Award? Why did you decide to do that?
Well, yeah, as we discussed, before joining the lab at the University of Pittsburgh, I was not into the BCI community. So I was completely an outsider. And I'm not saying that the BCI community is a clique, but it's a well-established community with its celebrities, its methods, its conferences. So it was a bit intimidating for me to join this BCI community from the outside. And I remember at one conference at SFN, I think in Washington, there were some people asking Jen Collinger for selfies or for autographs. And I was like, wow, I'm really working with important people. I'm really working with bigwigs in here, which made it a bit scary and intimidating for me. I had Zoom meetings with plenty of celebrities of the BCI community. And I think that applying to this award, it was a way for me to confront my ideas and to be able to show them to the community. And I think it worked well. It worked well because the presentations and the announcement of the BCI Awards, it took place exactly during the last SFN conference. And so I was in my hotel room during the presentation, and right after I went to the conference center and I had the opportunity to discuss with the other people who got awarded, which are actually people from the University of Chicago that I had Zoom meeting with regularly, but I never had the opportunity to in-person exchange with them. So it was really cool.
Yes, yes. Thank you for mentioning that. Because what you are saying is if you are new to the field, well, you can apply for the award. And this is one of the ways. Yes, not all, but one of the ways how to connect with the community, how to network, how to get to know people. And yeah, that's a great instrument for doing that. Any suggestions do you have for people on how to make their submission successful? Because yours obviously was, yes?
I would say try not to be obsessed with awards. That might be counterintuitive, but try not to be too obsessed with awards. In general, in science, there is a lot of frustration. You are going to apply to a lot of stuff, to a lot of position, to a lot of awards, to a lot of conference, to a lot of journals. And 99% of the time, you are going to get rejected. You are not going to get an answer. You are going to be answered no. And it's fine. This is how science works. What matters is not the 99% of the rejections. They don't mean that you are doing poor science. They don't mean that you are not a good scientist. What you need to focus on is this 1%. Simply because this is very competitive. So you should not be let down by papers being rejected, by an award that you missed, or that kind of stuff. As for the application itself, I would say the best way, and this is true for an application to the BCI Award, for an application to a position, for a new grant submission, or for a new paper, have as many people as possible review it, because they are going to be able to tell you whether it's clear, whether the novelty is well highlighted. So whatever you need to submit something, whether this is for the BCI Award or for something else, just trust your peers and have them give you suggestions. It's also fine to judge that some of your peers are not going to give you constructive feedbacks. And I think this is the way you grow as a scientist. At first, you are going to take everything that is sent at you, you are going to take it personally. And then as you grow up, you're going to think, oh, maybe this feedback was not very constructive. Maybe it's fine to just ignore it, which is fine. So yeah, whatever you try to submit, try to have the feedbacks of your peers.
Great suggestion. And another question is our podcast is called Neurocareers, Doing the Impossible. Was there anything in your life or in your career that you think of as impossible, but you actually made it work, made it possible? And how did you do that?
It's very slightly BCI related, but I'm going to give it a shot. As I said, before joining academia and before starting my PhD, I had a training in engineering, and especially in space engineering. Before being a brain nerd, I was a space nerd. So I got my master in engineering, in space engineering in France. And before joining academia, I've been working for 2 years in the industry with Airbus in France. And what I've always dreamt of was to become an astronaut. Very luckily, I've been able to successfully fail twice for an astronaut selection, the 2016 Canadian one and the 2022 European ones. I'm not deterred. I'm going to try for the next ones. But something that is very cool also is to do some parabolic flights. So I don't know if you've heard these parabolic flights. taking place in big airliners, following these kind of trajectories in order to have a few seconds of microgravity and to do microgravity science. And so I've been selected as a participant for one of these flights just a few weeks ago. And very interestingly, there was a team in the plane doing an EEG experiment, just analyzing how your brain and your brain activity, and especially your EEG activity, is impacted by microgravity or hypergravity. And very interestingly, the equipment was lent by the very same company that is organizing the BCI Award.
Yeah, GTEC. Yes, GTEC company.
Yeah, everything is related. Exactly. Yeah, it was funny for me to see the GTEC sticker on the plane. I was like, I know this guy.
Yes, that is absolutely amazing. What calls you into space?
Because it's cool. No, I would say, yeah. I would say space research, this is still a way to apply theories and to try to build concrete problems. Plenty of technologies that were developed for space then found out to have some concrete applications on Earth. And this is something I would like to contribute to.
Yes, that is amazing. And of course, I wish you all the best and in your space journey and in your BCI journey. You are doing amazing things. And I think the very important note from this podcast, and thank you for that, that things can be done gradually, but they really create results. So thank you.
Take your time, focus on doing good science. Never forget that we are insanely lucky to be paid to do science. Never forget to have fun doing science. Just take your time, keep good ethics, keep good results, and it's going to come along.
Thank you so much. Camille, what is the best way for our listeners to learn about the work you do and connect if possible?
Probably the best way is to check regularly the website of the Institute. It's called INRIA. There is a website discussing the different improvement that we are doing. Our labs is still in the process of its creation, so probably plenty of news are going to pop up recently in the future.
Yes, and probably people can connect with you on LinkedIn. Is that, yes, you're
Sure.
on LinkedIn. Oh, okay. Yes.
Of course.
Wonderful. Very good. So I've asked you quite a few questions. Is there anything that maybe I didn't ask you, but you still would like to share with our listeners?
I don't think so. Yeah, you asked this question about what specific figures I have in mind as an inspiration in science.
Yes.
I'm sorry, I don't think I have any. There are a lot of people that I found really impressive, but I think it would be very unfair from me to say, hey, I really prefer Marie Curie over Albert Einstein. I don't think that would be fair of me.
Mhm.
We are all sitting on the shoulders of giants, and I don't want to pick just one single one.
Yes, and that's a beautiful response as well. Thank you. Thank you, Camille. It was a true pleasure to interview you. Dear Neurocareers podcast listeners, thank you for joining me and my incredible guests on this exciting journey into careers in neuroscience and neurotechnologies. I hope you've been inspired by the stories of those turning groundbreaking ideas into impactful realities. If you are looking for more guidance on advancing your neurocareer, book a free consultation with me, Dr. K, your podcast host and neurocareers coach at the Institute of Neuroapproaches, the only career service dedicated specifically to the needs of professionals in neurotech. Let's take the next step toward your neurocareer success together. In addition to free consultations, the Institute of Neuroapproaches offers a variety of services designed to help you thrive in neurotech. First, professional development planning. We help you create a tailored career development plan, identify knowledge gaps, and equip you with the tools needed to achieve your goals in neuroscience and neurotechnologies. Second, resume and cover letter review. Get expert feedback on how to craft documents that are specifically designed for job opportunities in the neurotech field. Third, interview preparation. Sharpen your interview skills through mock interviews and targeted feedback, including soft skills, hard skills in neurotech, BCIs, e.g., MEG, live coding, and presentation preparation. 4. Networking and job search strategy. Learn how to effectively network and uncover job opportunities while standing out in the competitive neurotech job market. 5. Negotiation and salary advice. Receive expert guidance on negotiating salaries and benefits and determining a fair salary range for your desired position. All this and more can be found at www.neuroapproaches.org. Again, www.neuroapproaches.org. So, what are you waiting for? Let's navigate the path to success in the world of neurocareers together and turn the impossible into possible. We're looking forward to working with you.